So now that we know our special right triangles and we know a little bit about right triangles, we are going to move on to incorporate some of that information and look a little bit more at right triangles with trigonometry. So, first of all, the word trigonometry comes from a Greek word that means the measurement of triangles. So that's where trigonometry started, was measuring triangles. So if we look specifically at right triangles, so all the triangles we're looking at are going to be right triangles. And we start with a reference angle, an angle that we're going to relate everything to. So if I start with this angle right here at the top of this triangle, and this is my angle of reference, then I can name all of the sides of my triangle in relation to that angle. So I first can name the adjacent leg. So the leg of the triangle, which is adjacent to this angle. So I have two legs of a triangle, over here on the right and down here on the left. And the one that's adjacent is the one that's touching or next to that angle, which would be this side here. I also have then the other leg, which is the opposite leg. It's the leg across from the angle. So this is my opposite leg. And then of course, like we have in every right triangle, the side opposite the right angle here is going to be my hypotenuse. So in every right triangle, pick an angle for reference, one of your non-right angles, and you can label the adjacent leg and the opposite leg. And the hypotenuse is always across from that right angle. Okay? These are labels that we are going to have to use to look at our basic trig functions. And that's what we're looking at today, our basic trigonometry trig functions. So what are those trig functions? To help us find missing parts of triangles when we can't use Pythagorean theorem, we use these trig ratios. The sine is the ratio of the measures of the opposite leg and the hypotenuse. Okay, we're going to simplify the words here in just a minute, but that is the ratio, which we call sine, S-I-N-E. We also have cosine, which is the ratio of the measures of the adjacent leg and the hypotenuse. So notice we're already using those labels, opposite leg, adjacent leg. And then we use them both here for tangent, is the ratio of the measures of the opposite leg and the adjacent leg. So you may be thinking, well, that's a lot to remember. How am I going to remember all these ratios? So we're going to simplify it a little bit for you. Let's take those ratios and just write them out as, instead of in words, as a ratio. So if I take sine, and we abbreviate sine, we take off the E and just make it S-I-N. And I abbreviate my sides, opposite over hypotenuse. The ratio of opposite leg to hypotenuse. I can do the same thing with cosine. We abbreviate cosine by taking off the I-N-E and just making it C-O-S, cos, the first three letters. And that is the ratio adjacent to hypotenuse, so adjacent over hypotenuse. And then for tangent, our tangent ratio is opposite to adjacent, so tan for tangent equals opposite over adjacent. So we can shorten it that way, shorten the words a little bit. And then we can even shorten it further. Let me take out most of those words and just leave me with the first letters. S for sine, C for cosine, T for tangent, O for opposite, A for adjacent, and H for hypotenuse. And then I'm going to smush those together. If you've ever heard someone say SOHCAHTOA, this is what they're referring to. If you've never heard anyone say that, well, get used to it. SOHCAHTOA is what we use to remember what these ratios are. Sine equals opposite over hypotenuse. Cosine equals adjacent over hypotenuse. Tangent equals opposite over adjacent. And so if we just remember SOHCAHTOA, it's a really short, easy way for us to remember what these ratios are. So when you know the ratios, when you have them memorized, then we can use them. Okay, so you may be asking yourself, okay, great, SOHCAHTOA, what does that do for me? Here we go. When we refer to angles in a triangle, we use Greek letters. So the three of the most common we use are alpha, beta, and theta. So when you see these, they're referring to the measurement of an angle in degrees. So alpha, beta, and then theta. And sometimes theta's got a curly Q on top. Okay? And so you're going to see those in triangles to refer to an angle. So I want to write sine of alpha, cosine of alpha, and tangent of alpha as fractions. So alpha is my angle. That's this angle right here. And I want to write the ratios, sine, cosine, and tangent of that angle as fractions. So in this triangle here, the sine, if we remember, sine of alpha, so remember your ratios, so is opposite over hypotenuse. So my opposite is 8. My hypotenuse, across from the right angle here, is 17. That's not opposite. Hypotenuse. And my adjacent side is 15. And so opposite over hypotenuse is 8 over 17. I can't simplify that fraction, so that is my sine. For cosine, cosine is adjacent over hypotenuse. Remember, so, ca, toa, that's my ca, C-A-H. Cosine is adjacent over hypotenuse. And so adjacent is 15. Hypotenuse is 17. Again, I can't simplify that fraction, so that's my answer. Last, we'll do tangent. Tangent of alpha equals, remember, so, ca, toa, T-O-A. So opposite over adjacent. So opposite is 8, adjacent is 15. Can't reduce that fraction, so 8 over 15. These are my 3 trig ratios for this triangle, for this angle alpha, whatever that angle alpha is. Okay, so I don't need to know the measurement of alpha to write my trig ratios. I just need to know my side lengths. Okay? However, sometimes we know our angle and we don't know our side length. And so that's when we can plug in different pieces of information to our ratios to solve for something that I need to know. So let's look at an example here. If I have this triangle, it's a 40, 50, 90 triangle. Nothing special about it, other than that it's a right triangle. If I want to find the value of x, I could use 2 different equations to solve for x, which is what we're going to be doing here today. So let's write just the 2 equations. That's all we want. We don't want to solve, we just want to write the 2 equations. So pick an angle for reference. So first I need an angle. I'm going to pick my 40-degree angle. So from that 40-degree angle, I label all my sides. This one is my adjacent. This is my opposite. And this is my hypotenuse. Okay. Notice I don't have a value for opposite, so I'm not really going to be able to use it. But instead, I can use my adjacent and my hypotenuse. So using my 40-degree angle and my adjacent and hypotenuse legs or sides, which trig function uses adjacent and hypotenuse? So if I think SOHCAHTOA and even jot it down on the side of my page, I'm looking for A and H, which are right here. So I could use the cosine of my angle equals adjacent over hypotenuse. I can use this formula. Notice the only thing that I don't have is x, right? Cosine 40 has a value. I don't know what it is. You don't know what it is off the top of your head, but it does have a value. So I can just write this formula, and then my next step would be to solve. Okay? We're not there yet, we're just writing the formula. Notice it says two different equations. So I could use a different equation. Not with angle 40 because all I have is adjacent and hypotenuse. But if I use angle 50 as my reference, let me relabel. This side would be adjacent. This side would be opposite. And then, like always, hypotenuse. So in this case, my adjacent side I don't have, but I have opposite and hypotenuse. So in my SOHCAHTOA, I would be using sine. So the sine of my angle 50 is opposite, x, over hypotenuse, 12. So I could use either the cosine of 40 or the sine of 50 to solve for my unknown side, x. Okay? The reason I point this out is to show that complementary angles, like 40 and 50, the cosine of one is the same as the sine of the other. And we can see that here because what switches is the opposite and the adjacent. And so what changes opposite and adjacent in my SOHCAHTOA? What else, which ones have everything else the same except that? And that's sine and cosine. So if I switch opposite and adjacent, then I'm switching from sine to cosine. Hopefully that sort of makes sense to you. Okay? So this is a basic introduction to the trig functions. We do have examples. I'm going to put those in another video. This is just a straight example of what the functions are, how you write the function itself, and then a first start to equations, which is what we're going to solve in the next video. So look for the next video, which is going to have solving these types of equations to find the missing parts of a triangle.